Good afternoon, everyone. Today, we will talk about applications of second law of thermodynamics. Okay? And I will recall some graphs and processes that we covered for first law for closed system and open system applications. And we're going to introduce a new diagram. We know how to, I assume you know, how to sketch diagram on a PV and TV. Now we will introduce a new diagram which is TS, and we're going to compare them. So applications of the second law of thermodynamics for pure substance. So last time we introduced TdS equations. TdS plus Tv, and we had a second equation TdS, TH3dV. Okay. Today we will talk about pure substances. And as we know, what we did for first law application on a closed system and open system, we were extracting properties from the data, from a table, right? Same rule, we will just add a new property, which is entropy, right? We can still read those properties from the table. Same way we did for first law, open system, and closed system. Okay? Pure substance. Pure substances and a TdS diagram. Y-axis is usually for temperature, Celsius or Kelvin, and the x-axis is for entropy, the joules kilogram Kelvin or Celsius. Remember, from a PV diagram, same rules, same region, everything is same. On a TS diagram, this curve looks metric. Okay? On a PV diagram, it leans towards the pressure side, remember. So on this, let's remember this critical point, okay? Same thing. Critical point. Saturated liquid line. Saturated vapor line. Right. Same thing, everything is same. Remember when I introduced PV diagram, I said PV diagram is a 2D slide of 3D version, right? Temperature, pressure, and physical. Right. Same thing we are looking at TS here. And let's draw another diagram to make it clear. Entropy. And temperature. Left side of the saturation liquid was compressed liquid. Under the curve is wet vapor region. And the right side is superheated vapor. As I said, same rules are valid for second law of thermodynamics as well. We will still be using tables for extracting properties or data for what we did for first law, open system and closed system. Yeah. Compressed liquid. We will not have a separate table for compressed liquid, as you know. Right? Same thing. We might have, but it will be very broken. And it will not be detailed table for in terms of extracting properties. Compressed liquid, saturated liquid, wet vapor region, saturated vapor, and superheated vapor. And we have still same processes we are dealing with, and we want to introduce new processes because due to second law. So isothermal, right? With what? Constant temperature, right? Isobaric, constant pressure. Isometric, constant volume. Isentropic, constant entropy. Isoentropic, constant entropy. You may not say this, but isoenergetic. Okay. Pressure versus specific volume. PV diagram and TS diagram. Temperature, Celsius, kilogram per Kelvin, and bar, union leading. PV diagram, TS diagram. Okay. Let's look at the isothermal process first. Isothermal. Remember, isothermal process on the PV diagram with a linear decrease on a compressed liquid region, constant under the saturation dome, unless it is stated, unless you are stated what the behavioral it is, and quadratic or synthetic on a particular region. It could be either direction. Isothermal on a TS diagram, right? Constant, because the temperature is constant. Okay. So be careful when you work on specific diagrams, you will change. Second one, isobaric. Temperature, schedule, kilogram Kelvin, kilogram, pressure. All right. Okay. I assume you know how pressure looks on a PV diagram, right? Isobaric process, the straight line, the pressure is constant, right? It looks up or down slope on a TS diagram. Compressed liquid region, wet vapor, and superheated. Okay? These are both isobaric processes. One on a PV diagram, other one is on TS diagram. Careful, this is not a TV, TS. Okay? And we also have TV. Isometric. And kilogram, pressure, and bar. Kelvin, temperature. Isometric process, right? Constant volume. How would it look on a PV diagram? The vertical line, correct? Vertical. On a TS diagram, right, it will look upper sloping line. Um, Kelvin, kilogram, and pressure in bars. Isentropic. constant entropy. Or isentropic. We didn't name this as an isentropic when we first started working on PV and CV diagrams. We said adiabatic. Okay. Remember, Q is 0 if the Q is 0, right? In the adiabatic case, and remember the delta S equals delta dQ over T. Right? Isentropic. Delta S is 0, which means the Q is 0 because T cannot be 0. This is also called adiabatic. Okay. So adiabatic, I know stiffer line, stiffer curve on a PV diagram. And it will be vertical straight line on a TS diagram because S is constant, entropy constant. Any questions? Example. Two kilograms of steam expand adiabatically from state 1, where pressure is 10 bar, temperature 500 Celsius, to state 2, where pressure is 1 bar and temperature 200 Celsius. A, do these values violate the second law? How do I check my validation of the second law? Anyone? We just said it's not that. Efficiency? What if I can't find my efficiency? What is it? Yeah. What was it? Efficiency is one way. Entropy production. Okay. Remember, that term has to be negative. Has to be negative to make it negative, but the entropy production is always positive. If you have a negative, you're violating your second law. That's another way of checking it. Okay? B, if not, calculate the work. C, if the processes were reversible, between the initial state and the final pressure, calculate the work and the final temperature. D, of course, sketch process line on a TS diagram. For the actual and for the reversible processes. Okay. So we don't specify, or we are not looking at specifically on a closed system or open system. This is general. Okay, we already covered closed system and open system. Okay? There's no distinguish, right, in this case. Since we covered all those cases, I assume that you know how to treat closed system and you know how to treat open system. We are just introducing entropy approach, second law approach to those cases. Okay. So we have a system which is closed in this case, and it's adiabatic, right, where Q is 0. Right. The problem statement, it says that pressure at the state 1 is 10 bar and temperature is 500 Celsius. And system expands to a second state where pressure is 1 bar and temperature is 200 Celsius. To verify second law first, case A. For second law, right, if Q is 0, right, delta S is bigger than 0 or equal to 0 at max or minimum in this case. Okay. So I need to check my entropy from state 1 to state 2. I can find my properties at state 1 and state 2 because I know what pressure and temperature, correct? So for, okay, let's put it here. Internal energy at state 1 is 3,124.4 kilojoules per kilogram. Okay. Entropy at state 1, 7.7622 kilojoules per kilogram Kelvin. Okay. Internal energy, you can also find enthalpy, specific volume, and etc. You can do those actually if you would like to. So internal energy at state 2, 1 bar, 200 Celsius, internal energy will be 2,658.1 kilojoules per kilogram. Entropy at state 2 is 7.8343 kilojoules per kilogram Kelvin. I know my entropy for each state, state 1 and state 2. I can, which I can, find the difference, I can see if I'm violating my second law. Okay? Because I know the condition here. It gives me negative, I'm violating, correct? So state 1 to state 2, S2 minus S1, that should give you 0.0721 kilojoules per kilogram Kelvin. So, good. So second law is satisfied and process is reversible or irreversible. Reversible? Why is that?
There's no, well, actually, I'm not sure, but there's no friction because delta S is greater than zero.
Delta S is not equal to 0. I just found it. Greater than 0. Which makes it irreversible. Not reversible. System being adiabatic doesn't mean reversible. Okay. It might be adiabatic and irreversible. Might be adiabatic and reversible as well. Okay? So be careful with those. Okay. B. I'm asked to calculate work. Q, this work equals delta E, right? Stored energy in the system. Q in this case is 0, right? Work from state 1 to state 2 will be equal to minus M U2 minus U1. I know my U2, I know my U1, and I also know my mass. It's given in the problem. So work from state 1 to state 2 will be minus 2 kilograms, U2 2,658.1 minus U1 3,124.4 kilojoules per kilogram, and work from state 1 to state 2 is 932.6 kilojoules. Okay. On the problem statement for C, if the process were reversible, right? We showed that it's irreversible, it's not reversible, but we are going to assume that it's reversible, okay? Where delta S is 0, all right? So between the initial state and the final state, calculate the work in that case and find the pressure, because we assume that it's reversible, our final state will change. State given in the problem is for irreversible. If I change the condition, the last condition will change, or vice versa. See? Reversible process from state 1 where pressure is 10 bar, temperature is 500 Celsius, to state 2 where pressure is 1 bar. Okay? So under this condition, I'm asked to assume that delta S is 0, right? Which means S1 will be equal to S2. but that wasn't the case before. I'm changing it. Right? S1 equals S2, and I know my S1 from the given conditions at state 1. S1 was 7.7622 kilojoules per kilogram Kelvin. Okay. Now I go back to my table, and at a given pressure at state 2, okay, I knew my temperature, but I don't know my temperature for reversible case. I know my temperature for irreversible. But now I know my entropy for reversible case. And I also know my pressure. Okay. Now I can go to table and see where this property corresponds to what temperature under that pressure. Okay. Clear? Okay. So I'm gonna call this, right, U2S. S stands for reversible condition. Okay. Calls U. And I'm going to check this internal energy for pressure at state 2, which is 1 bar, and entropy is 7.7622 kilojoules kilogram Kelvin. For internal energy at state 2, reversible state 2, from table at 2,597.8. This is what I'm doing is interpolation. Okay. I'll show you in detail. 7.7622 minus 7.6597 divided by 7.8343 minus 7.6597, right? Times the internal energy difference between those temperatures. And 2,658.1 minus 2,597.8 kilojoules per kilogram. Internal energy for a reversible process at state 2 will be 2,633.2 kilojoules per kilogram. Okay. You can go ahead and check your tables to see what I did. What I did was basically find my entropy value at that pressure. Okay? And you will notice that it's in superheater region and it's between two temperatures. And I did it for internal energy. And I'm asked to calculate my temperature for a reversible process. T2 reversible, right? 160 Celsius plus 7.7622 minus 7.6597 divided by 7.8343 minus 7.6597 times 40. 200 minus 160 Celsius. Okay, this will give me my final temperature at state 2 for reversible process. Is 183.48 Celsius. Now I can calculate my reversible work. Okay. Q from state 1 to state 2 to S minus work from state 1 to state 2 reversible equals LPU. Okay. System being adiabatic doesn't change. Being reversible or irreversible doesn't affect adiabatic conditions. Okay. Q is still 0. Work from 1 to 2, right? State 1 to state 2 for reversible minus M U2S minus U1. I know everything to find my reversible work. Your reversible work minus 2 kilogram U2S 2633.2 reduced per kilogram minus U1 3124.4 reduced per kilogram. And work for reversible process will be 982.4 kilojoules. What was it before? 932 something. This makes sense. Right? Okay. So that means that I'm losing 50 kilojoules because of irreversibility. Okay. Notice that I'm producing work here. It would have been other way around if I was putting the work. Okay. Okay, let's everyone try by yourself. I will give you a minute or two to sketch a PS diagram. Okay, let's see what you do. And then I will show you. PS. Temperature versus entropy. Kilojoules, kilogram Kelvin, and temperature. And I want to show both processes, irreversible and reversible, on the same diagram. Okay.
Also, you, yeah, so
Okay. What do I do first? What is my first thing to put on this diagram? Curve. If you don't have curve, your point don't mean anything. I don't know if you're in compressed liquid, wet vapor. I don't know. Okay, that doesn't tell me anything. Okay? If you don't show the problem to anyone, let's say somewhere far, not in the United States, you're mailing to that person, to an engineer. If you send your graph, that person should be able to understand what you're trying to do. Okay? All right. Right. To start. And I know my phases now. Compressed liquid, wet vapors, saturated liquid, saturated vapors, preheated. How? From the given conditions for each state. Pressure, temperature, entropy, whatever it is given. Okay? I check my table and I know I am in superheated region for both cases. State 1, state 2, both for reversible and irreversible. Okay? So my point will be in superheated region. Okay? For state 1, the next question is, which one is 1? And how do I know? Top one is what? State 1, right? Because temperature has a higher temperature. Right? This is 1, this is 2. 2 for what? I have 2 2s. 2 reversible or 2 irreversible? What? Correct. So there's no change in entropy. State 1 to state 2, right? State 1 to state 2. Right? What about for irreversible one? For irreversible state, where is it? I know it's somewhere around. Well, where is it? Hmm? Is it on the left or right? Right? Okay, why is it on the right? Entropy increases. So everything I am doing, it makes sense. If it doesn't, think again. So now I'm higher than 2 or lower than 2? Higher because temperature is higher, right? So this is 2s, this is 2. So here's the thing. On diagram, reversible process is a straight line. Okay? For irreversible, the dashed line. Okay, that's it. So we are done. Any questions on this? No? Okay. This one. Okay, let's solve one more problem. Example. The quantity of refrigerant 22 contained within a piston cylinder assembly undergoes process from a state where the pressure is 6 bar and the quality is 50%. I'm moving this state to a state where the temperature is 16 Celsius and the refrigerant is saturated liquid. A, determine the change in specific entropy. B, can this process be accomplished adiabatically? C, sketch the process on a TS diagram. In the previous problem, when I sketch, I forgot to show that adiabatic, right? Meaning that it's insulated. Right? I stated it, but I didn't show it on the sketch. Yeah, sorry about that. Okay. Closed system. I have refrigerant 22 for 1 kilogram mass. I'm going from state 1 to state 2. State 1 conditions, pressure is 6 bar. Temperature, I don't know. X, 50%. To your temperature 16 Celsius, second state, and X is 0. Okay. Pressure 6 bar, yes.
How do you know it's 1 kilogram?
Oh, a second, let me check. Good question. I don't. Or I'm missing the statement. I don't. I don't know. Well, we can either know. I don't know. Sorry.
Whatever.
A quantity. No. But we don't know the kilogram. Okay, we don't know the mass. It shouldn't affect the result. Okay. Thank you. All right. So I can find my properties at state 1. Right. S1 is I'm asked to determine the change in the specific entropy. Right. S1 from table would refrigerant 22 table, and you are given the condition 6 bar 50% with the 50% quality, right? Which means I'm under the saturation pressure, right? So S1 will be 0.2019 kilojoules per kilogram Kelvin. Right? For 50% quality, 0.9186 minus 0.2019 kilojoules per kilogram Kelvin, and S1 from here 0.56025 kilojoules per kilogram Kelvin. Specific entropy change from state 1 to state 2, S2 minus S1, right? S2 for a given temperature at a specific, the saturated liquid is 0.2442 minus S1, a specific entropy at state 1, 0.56025 kilojoules per Kelvin. And entropy change from here, S1 to S2. Step 1, state 2 is minus 0.31605 kilojoules per Kelvin. E, can this process accomplished adiabatically? No, okay? Because delta S is negative. Okay. So since delta S is less than 0, this process cannot be accomplished adiabatically. Kilojoules kilogram Kelvin and temperature. Right? I'm going from here to here. Okay, any questions? Okay, let's continue. Example. An insulated vessel is divided into two compartments connected by a valve. Initially, one compartment contains steam, 10 bar, 500 Celsius, and the other is evacuated. The valve is opened and the steam is allowed to fill the entire volume. Achieving a final pressure of 1 bar determine a final temperature in Celsius, E, the percentage of the vessel initially occupied by the steam, C, the amount of entropy produced in kilojoules, kilograms, Kelvin. Okay. I have an insulated vessel divided into two compartments, right? And it's insulated. One part is created, and other section has steam contained in the system at 10 bar and 500 Celsius. And final pressure after we open the barrier is 1 bar. At state 1, 10 bar, 500 Celsius, I can find my properties: specific volume, internal energy, entropy, also enthalpy. And specific volume for state 1, before I open the valve, is 0.354 meter cubed per kilogram. Internal energy 3,124.4 kilojoules per kilogram. And entropy at state 1, 7.7622 kilojoules per kilogram Kelvin. Insulated, right? Q is 0. The work is also 0. It has a rigid wall. Right? There's no change in the wall. So it is in the state, but not in the overall volume. Okay? Which makes U1 equals U2. Okay? I know my U1, which is equal to U2. Okay? U2 will be 3,124.4 kilojoules per kilogram. And I also know my pressure, the final proof, 1 bar. Now, I can find my condition. Right? At 1 bar, with that internal energy, what is my phase? Right? I can determine my phase. And to determine my phase, I can find my temperature. It's in superheated. Okay, I will leave this to you to do the interpolation part. Okay, I will give you the final result, but try to find that final result by yourself. Specific volume, entropy. If you can't find it, let me know, I will explain. Temperature 495.64 Celsius. In turn, specific volume 3.545 meters cubed per kilogram, and entropy 8.8218 joules per kilogram Kelvin. Okay. All you need to do is interpolation. Okay. I think that will be a good practice. It's a closed system, or that means what? My mass doesn't change, right? For the volume comparison, I can compare my specific volume. Right? Because mass is same. Mass will cancel out anyway. For A, volume ratio, volume 1, volume 2, before and after the valve is open, is literally the specific volume ratio, because mass is constant. I know my specific volume at state 1.35 per meter cubed per kilogram, and specific volume at state 2, 3.54 meters cubed per kilogram. V1 over V2 will be 0.0999. So approximately 10% of the vessel volume is initially occupied, correct? P, that was P. Temperature is A, right? And now it's C. Entropy production. Entropy production delta S equals integration of dq over T plus the entropy production sigma. Remember, sigma equals Q minus S1, right? Integral dq over T. And entropy production I know my delta S, and I know this integral. Well, what is it? 0. S2, 8.8218 minus S1, 7.7622 kilojoules kilogram Kelvin. So entropy production is 1.0596 kilojoules kilogram Kelvin. Any questions about this? I will leave this to you, the diagram, okay? But please work on this and let's look at it next class.